As you've already seen in the homework, um, there are questions that you have to think through carefully about how to apply just the raw basic concepts to any kind of structure of a problem. And sometimes those questions can seem subtle. Um, Oddly enough, if you crack open like a statistics textbook or something like that, um, you really won't find much about how to think through those kinds of issues. What you'll find are, theorems and uh, discussion of the fine points of this statistical theory, but the question of how to apply it to real problems is usually left kind of, as a exercise for the reader. It's implicit rather than explicit. So what I actually want to do over the next few classes is try to become very, very explicit about how to think about building probabilistic models for real-world problems. And as a point of departure, you can't do much better than what Einstein said, make everything as simple as possible but no simpler, which of course, is trivial to say, but the actual doing is where all the genius lies. One basic way of thinking about that is that clearly you have to start with something that you can understand. You have to be able to take whatever it is that you do understand or feel capable of understanding at that moment and make it explicit. Draw a picture of it, write an equation for it, do something that captures the essence of what you think you can understand about a problem. Of course, there is a possibility that that will not be enough to take you all the way to the end goal, but there is very often a sort of 80-20 rule in probabilistic modeling. That is to say, you can oftentimes capture sort of 80% of the phenomenon of interest with only 20% of the complexity of model structures. So even if it turns out that that model is not completely adequate for everything that you eventually want to be able to do, it's probably a really good first step to build that model, see how it matches up to real data. So the basic idea here is start simple, be very explicit, write out what you think is a basic way of capturing the essence of what you're trying to model. And then, of course, you're going to have to later on go and check very explicitly through probabilistic tests that we're going to be talking about in this class how well it actually is doing at capturing, predicting your real data. When we say define a core problem, what we really mean, of course, is choosing simplifying assumptions that cut away a vast swath of all of the possible complications that might be going on in your data, but of course also might not really matter for what you're doing. We've seen already examples of these simplifying assumptions. For example, when we were talking about inferring from sequencing data of mutant bacteria to try to figure out which gene is likely to be the cause of the phenotype that was selected for, there was an implicit assumption there that the process of mutation is essentially uniform across the genome coordinates, right? In other words, that the probability that a mutation occurs in any given location is, to a first approximation for just beginning to think about the problem, you could say, well, let's assume that it's equal, it's uniform. And then that helps us think about what the essence of the problem is. Of course, when we actually go do a computation, we probably will want to take into account various factors that can create non-uniform mutation probability, but we can probably factor those in very cleanly into our original model basically by, for example, transforming the raw genomic coordinate system instead into another variable that basically takes into account the effective target size of any given gene for real-world mutation probabilities. For example, there's all sorts of biases in the targeting of a particular chemical mutagen so that it's more likely to hit certain nucleotides compared with other nucleotides, and that's something that can be taken into account in calculating sort of an effective target size for any given gene. How likely is it to be mutated under the random probabilities and biases of a given mutagen? Okay, so we're going to start by thinking about what assumptions we should use to simplify a problem. And we're also going to proceed to thinking about how to simplify the handling of our observables as well. You could think of this part to a certain extent as being about the hidden variables. In other words, what really matters inside the black box that is emitting our observations. And you could think about this part as being about the observables. Oftentimes, especially depending upon the particular model that you're choosing in that first step, there are huge simplifications that we can make for how to handle our observables. And we'll talk about that basic idea, the so-called concept of a sufficient statistic, basically being that we can boil down our raw observations into a much simpler form that will be a lot easier to work with, basically because it fully captures the information that are present in our original observations that is relevant to the model that we're using. Okay? We'll make all this explicit as we go along. Okay, so what are the pieces of this process? Well, they're pretty much the pieces that we've already talked about. We're going to have random variables, and we're going to have probability distributions that connect different hidden and observable variables. So it's very much the structure that we've already talked about, but now we're just going to become a bit more explicit in how to think about that as a structure. So basically what we're going to spend some time on actually is kind of the picture piece of this puzzle. You'll recall at the beginning of the class I said, words, pictures, and equations were three different sort of superpowers that people have. And here we're actually going to talk a little bit about how to make pictures of problems in a very explicit, formal way, basically as a graph structure whose nodes represent random variables and whose edges represent non-zero information connections between variables. It basically captures the conditional independent structure of a specified model. That's the intuitive version of how to talk about it. We'll become very specific and explicit in a moment.